All right, sorry folks, a little bit of pause there. Just gonna turn up the brightness on this so it looks a little bit brighter for you guys. Okay, so this is the final lesson of chapter 1, the infinite geometric series. Again, all of these can be used as standalone. You don't have to do anything prior to doing this lesson. This is standalone, but the other lessons, they build on each other, but they're not they don't build on each other. They're not required in order to jump in at the last lesson. Okay, so now we're talking about infinite geometric series. Okay, infinite means never ends, and I think we all probably could have guessed that. Geometric, if you haven't done any of the other lessons, geometric means you multiply to get to the next term in the pattern. Series just means we're summing them all together. So we're adding them all together. So I just want to point out, like if we had 8, 4, 2, 1, next one would be 1/2. That continues on forever and ever and ever. There's no stopping. That's what the ellipses mean, the 3 dots. So to get from here to here, you're probably saying, hey, I need to divide by 2. But in this, we're talking about multiply. So everything is done in terms of multiplying. So what that means is we would have to multiply by 1/2. It's the exact same math as dividing by 2, but we're always talking about how we get to the next terms in relation of what we multiply it by. Okay, now this one's a little bit different because this never-ending thing, this makes it a little bit tricky. So a convergent series, a series with an infinite number of terms, so obviously it can go on forever, which approaches a fixed value. The fixed value is always 0. So what that means is that the numbers are getting smaller and smaller and smaller. They'll never reach 0, but they'll get so tiny that it's really, really close to 0. So the number that the convergent series is always working towards is 0. So as you can see, we started at 4. This is a quarter. So we keep getting smaller and smaller and smaller. A quarter of a quarter is a 16th. A quarter of a 16th is a 64th. And you can see that the numbers are getting tinier and tinier and tinier. A divergent series, convergent means to move in. So move in on something. A divergent series means to move away from something. Oh, sorry, you can't see that. That just says move away. So a divergent, if you are diverging, you're moving away. So it does not approach a fixed value. What it's actually headed towards is the idea of infinity. Now remember that infinity is not an actual number, it's a concept. So you're diverging, you're getting away from your fixed value of 0 and you're going towards a concept. These numbers are going to continue to get bigger and bigger and bigger and bigger as they go along. Okay, this is the trick. Where's my highlighter? I don't know if you'll be able to see this. You can only find the sum of convergent series. You can't do it on divergent. The reason why we can, so the sum, we're adding stuff up. So we need to know that it's going to get eventually so small that it's going to be insignificant. Here it's going to get really, really big, and that's going to be too significant to estimate. All right, so if we hop to our formula sheet, there's only one option for geometric series. And remember, anything after the comma is just that restriction. So it's saying r has to be between 1 and -1. So really, those are all the fractions. So I'm going to write that out. So the sum of the infinite series is equal to T1 divided by 1 minus r, where r has to be less than 1, but greater than -1. So all that means is that if I had a number line, and this has a value of 1, and this has a value of -1, your numbers have to be in here. It can't include them because it doesn't have the equal to sign. So it has to be in this area of your number line. Can't include them, so we'd indicate that with open circles. I think you should remember that from grade 9. Maybe, maybe not. But open circles mean it doesn't include those points. It's everything in between. So essentially you're dealing with fractions that are smaller than 1. Okay, so let's define this. So S infinity is the infinite sum. T1 is the value of the first term. And R is your common ratio. That's how you get from, oh geez Louise, sorry guys, couldn't read that. That's how you get from number to number. So if I have R equals 1, 3, 9, 27, or sorry, that's not your common ratio. So if my series went like this, we can see that it's pretty obvious that I'm multiplying by 3. So my common ratio would be 3. But if you don't know how to if it doesn't jump off the page to you, I always encourage you to do the math. So I would take T2 and divide it by T1, or you could take T4 and divide it by the term that comes in front of it. It really doesn't matter. So T2 is 3, 3 divided by 1, so my common ratio is 3. Sorry, that equal sign shouldn't be there. My math is getting sloppier as the day goes on. That's not good. All right, and sometimes it doesn't leap off the page at you, kind of like this one. So decide whether each infinite geometric series is convergent or divergent and calculate the infinite sum if it exists. Okay, so what's going to tell us if it's converging or diverging? We have to find the common ratio. That will answer that question for us. So I'm looking at this, and this doesn't really jump off the page to me what I should be doing. So what I'm going to do is to find my common ratio, I'm going to take T3 divided by T2. It doesn't matter which set you take, but it has to be T3, then you divide by the term that comes before it. So I'm going to have a positive 1/9 divided by a negative 1/3. So the ratio is going to be 1/9 times negative 3 over 1. So R is equal to a negative 3 over 9. We're going to reduce that fraction. Sorry guys. We're going to reduce that fraction. So that's going to be negative 1/3. Okay, so knowing this, we know that converging has to go from negative 1 to positive 1. Has to be somewhere in here. And is negative 1/3 in here? If that's my 0, if this is a number line. So negative 1/3 would be about right there. So because it's in between those boundaries, we would say that this is convergent. And we know that we can take the infinite sum if something is convergent. So we're going to go ahead and use our formula. So S infinite is equal to T1 divided by 1 minus R. And again, if you've done the other lessons, the formulas are super similar. So please make sure you pay attention to what formula you're using. So we're looking for the infinite sum. Term 1 has a value of 1. We know our common ratio is negative 1/3, so 1 minus a negative 1/3. So S infinite is 1 over, so I'm going to say 3 over 3, so I just converted this to a fraction, plus 1 over 3, because subtract a negative number is going to give me a plus. So S infinite is 1 over 4/3. Now, the over part that I keep saying it as a fraction, really that just means divide in math. So we're going to have S infinite is equal to 1 divided by 4/3. We know we don't divide fractions, we multiply by the reciprocal. So we know that our infinite series is going to have a sum of 3/4. Pretty straightforward. This is, the trick with this one is just deciding whether it's convergent or divergent. And again, you have to know your common ratio in order to do that. All right, so looking at this example, I'm going to calculate my common ratio. So this time I'm going to take term 2 and divide it by term 1. You got to take the sign in front of it, right? So that's going to be -4 over +2. So that's going to be -2. Now remember that convergent happens between -1 and +1. Well, -2 is somewhere down here on this number line. So it's outside the boundaries of what's convergent. So this is divergent. It's moving away. So no infinite sum. So I actually can't calculate this one, but you can't leave it blank. I'm defining that it's divergent, and I'm making the statement that there's no infinite sum on divergent infinite series. So you have to make this statement. If you don't make this statement, I don't know if you know this. So just remember that you must make that statement. Okay, so that's page uno. That's a pretty light blue, so I'm gonna flip to a different color. Let's go green this time. Okay, so this picture represents an infinite geometric sequence. Assume that the black square represents 1/4. So this black square here is a quarter of this bigger square. Makes sense. So 1, 2, 3, 4. The pattern you can see is just continuing on in this square here. Okay, so write a series of terms that would represent this situation. All right, so let's start. Write a series of terms. So we're going to write them out. So A is, what are we starting with? We're starting with a quarter. Okay, and then this one, it is a quarter of a quarter. So 1/4 of a quarter. And then the next one is going to be 1/4 of what this term was. And if you do that math, that's 1/16. So that's 1/16 here. And if we did that math, that would be 1/64th. And that would be a quarter of 1/64th. And so on and so on and so on. So you're always taking a quarter of the number before. All right. How much of the total area of the entire square is shaded? First of all, we need to find our common ratio. And if you see it, you don't have to calculate it. But for those of us who can't see it, so term 1 for me was this. Term 2 was 1/16. Term 3 was 1/64th. I didn't multiply those because I'm just going with it. So I'm going to take 1/16 and I'm going to divide it by the term that comes before it. So that's 1/4. So this is going to be 1/16 times by 4/1. So R is equal to 4/16. I'm going to reduce that, and that's 1/4. So my common ratio is 1/4. And again, I'm looking at my number line here. So -1 to 0 to 1. So +1/4 is going to be somewhere around here. So that is within the convergent, oh, that's a bad. So that, anything in between these two numbers is convergent. So we can go ahead, this is a good number, so we can go ahead and calculate the infinite series. Remember that using the word series just means we're summing it. So S infinity is equal to T1, which is a quarter. 1/, yeah, that's the formula. Just want to double check. So it's 1 minus R. So I'm going to hop in here. So S infinite is equal to a quarter over 3/4. So we're going to have 1/4 divided by 3/4. I don't know if it makes, for me, it makes more sense to write it like this. And then I'm going to multiply by my reciprocal. So I'm going to have 4/12, which is 1/3. So my infinite sum is 1/3. All right. Okay, so this last example, I find sometimes people get a little hung up on the numbers and they're missing the point of it. Okay. All right, so this is an expanded, we know that when the line is over, whatever digits it's over, those are the ones that repeat. So 0.584 with the line over top of it is just 0.584, 584, 584. Okay, we can expand it so that it looks like that. Like if we have 346, we know that we can write that as we have 300s plus 40 plus 4 tens plus 6 units. You probably did that in elementary with like, these ones were the big squares and you did those and then you had 4 sticks. 1, 2, 3, 4, and then you had these little tiny squares that you probably used. And this is how you learned how to add or group like things together. This is how you learn to do it quickly. So you've done this, and when I show people this, they get all crazy about it. But essentially this is just this. It's just a different way to write it. If you add those all together, you keep going on up here. Notice the ellipses are happening. The ellipses are happening so that it just shows you that it continues on forever. Okay, so let's talk about determine the sum of this series. So I got to find R first. So this would be my T1, this would be my T2, this would be my T3. So I'm going to find R first by taking my T2 and I'm going to divide it by my T1 because you always take the term in front. Get my handy dandy calculator here. I prefer fractions. 0.00584 divided by 0.584. I bet you I could have done that in my head. 0.001. Now, we know that that is one, so that's tens, hundreds, thousandths. So we know that that is definitely on our card. If I were to put that into a fraction, that'd be 1 over 1,000. And that's our -1, our +1. And we know that that would be really, really, really close to 0. So that would be our 1/1000th. So it's still within that convergent restriction, okay? So now we're going to do our infinite sum. So our T1 was 0.5, that's supposed to be a 584 divided by 1 minus 0.001. So we're going to have 0.584 divided by 0.999. Okay, so I'm going to put that in my calculator. 0.584 divided by 0.999. And I'm going to get 0.584 repeating. Now in your calculator, I'm just going to show you my calculator for a second. You see that last digit is a 6. Don't let that mess with your head too much because your calculator is just rounding for you. It's saying, hey, I think this thing repeats forever, but I can't write forever down. So I'm just going to round it to a 6. So you have to be pretty, I know that dividing anything by 9s or 999 or 999 is going to give me a repeating decimal. So I knew that, so I know that this is repeating. This is kind of cool because it actually ends up right where you began and you're like, what's the point of doing this? It's just to show that when you're summing them, you're getting closer and closer back to that number. It's pretty cool. It's not all of them work this way. The repeating ones do, though, just a heads up. So that is your infinite geometric series. You have an assignment to go with it, and let me know if you have any questions. Thanks.